All right, everyone, welcome back again. So, today we are going to be talking about a special case of supervised learning, which is regression. And for the purpose of this class, we are going to be using R programming for the coding section. All right, so let's go. So let's talk about regression. In our previous class, we introduced you to machine learning, and then we break it down to different types where we talk about the supervised learning. And then we did talk about having two categories of that. We said we have the regression and then we have the classification. So today we're going to be talking about the regression in supervised learning. For any regression problem, what is the goal? What are we trying to achieve? At the end of the day, we're trying to build a model that can predict for a continuous outcome. Why? From one or more predictors. What we mean by this is we are going to build a model that can help us make predictions from a continuous. When we say continuous outcome, that's the response variable, that's the outcome variable with a set of predictor variable or a single predictor. Now, our choice of number of predictors now break down into two. When we have a simple linear regression, it means that we have a single continuous outcome and a single predictor variable. And when we have multiple linear regression, it's talking about having multiple predictor variable on a single continuous outcome variable. I hope that that is clear enough. Now, application wise, we can try to look at TV advertising versus the sales. We want to know whether the outcome variable in this case, which is the sales, can be influenced by the advertising techniques that you are using on the TV. All right. So another example will be education years versus lifetimes earnings. We want to see whether the number of years of education has any impact on the earnings of maybe anybody that has enough education in this so field. Does it have any significant effect, or can it be a predictor variable to their lifetime earnings? Also, the class size versus the GPA. So we want to know whether the class size has an impact on student GPA. So moving on, we are going to talk about simple linear regression for the purpose of this class. For today, we want to talk about simple linear regression. What do we mean by simple linear regression? We just talked about it earlier that we want to deal with just a single predictor variable on a continuous outcome variable. Now let's get into our notebook and then we can try to show one or two things in that regard. I'm gonna close some of this to make it wider and easier for us. All right, so when we say a simple linear regression, let's say SLR, right? And then we said under that we want to look at continuous. So for that we must have a continuous um we can have a continuous response variable, right? And then we are going to have just a single one predictor. So that means we're going to have a single y and we are going to have a single x. So for us to build our function, so we want a function that is just function of y equals to f of x. That's what we're trying to build. If you write this out, you can have y equals to beta naught plus beta 1 x. You don't even have to put, if you want to put x1, that's okay, but you're just saying a single x, which is a single predictor variable, plus the error. Because let's say you are doing this with respect to each of the outcomes we have, right? And then you have this. This is talking about what? This is talking about the intercept. This is talking about the slope. Now let's go back to our class so that we understand better what we are doing. All right, so we said this is a model of the outcome variable which is continuous on this intercept plus the slope of the predictor variable xi plus the error terms. Now we want to talk about error terms. Why do we need to add these error terms? The reason for that is we believe that this, when we model this, there are so many other factors that we cannot control, that this our predictor variable will not be able to capture it, and hence there's a need for a random effect, something that we do not have any control over, maybe some other influence that cannot be explained by the predictor variable. Then we need a random error to address that. Okay. So and then of course our high comes from 1 to n. It depends on the total number of observation. So that's what we have just said here. So what you see here is talking about the assumptions of the error term. And if you remember, one of the major assumptions of error term is that your mean of the error. Now we can come here and say, we can put this, let me change this to, so we can say assumptions of the error. So the first thing we want to talk about is the mean of the error terms. So we can say mean of the error, okay? And that's why we have expected value of EI must be 0. And then we can talk about the homoscedastic of the error, right? Of the error. So when you say the variance of the error must be constant, it must be constant across the error terms, right? So what do we mean by constant variance? Constant variance means that when you look at the points, when we are able to fit our error model, like let's say we try to visualize the error plot. The constant means that there should be no variability. They should have constant variability within the points. That's what it means. It means that when you look at it, because we have two of them, we have another one which is heteroscedasticity assumption, and that's when we violate the homoscede. So that's saying that you don't have a constant variance among the error terms. All right. So this we are going to show you how to check for this assumption before we proceed. All right, so the next thing we'll be talking about, we are going to show the chunks as well, because like I said, we are using R programming for the purpose of this class. So we need to show how to be able to run this in R. So we're using a publicly available data on which is an advertising data. If you go on this link, you can access it. And I'm sure in our previous class, we already talked about how to load in different type of data sets. It depends on which one. So we can import that data set using the CSV because it's a CSV file. Then we can do a little bit of just glimpsing on the data. You can use the glimpse function. You can use the structure function. We can use a lot of things just to view and to have an idea on our data, and then we can check the dimension of our data, of course. So the next thing we want to do is how do we estimate our parameters? Because remember, we are trying to fit a model like this. This is our continuous, this is our intercept, this is our slope, this is our predictor variable, and this is our error, okay? So when you have this model, the aim is for us to what? To model, to be able to estimate for the intercept, to be able to model, to find the estimate for the slope, and then that way we can see the relationship between the y and the x. But if we do not estimate for these two parameters, we cannot really see what influence one is having over the other, okay? So that's what we are trying to do here. Now, because we are using the ordinary least square, what's the aim? What's the goal of using that? We're trying to minimize the sum of square of error. Now, there's a whole lot of proving to show that, which we can do, but for the purpose of this class, we are not going to go that much into detail because we are restricting ourselves to a certain level, but maybe over the time we can try to look at that and show the proving. And it is actually simple to do. You just need to, because the aim of this is we're trying to minimize the sum of square of error. And what that means is that you can make your error the subject of the formula so that you have error to be what? yi minus beta naught minus beta 1x. When we say sum of square, what does it mean? It means that you are summing across the square of the error. So what that is saying is we are trying to find the summation of e square I, which is going to be summation yi minus beta naught minus beta 1 x all square. In fact, if you open this one up, it's quite simple. You're just going to have summation y, which is going to be what? So that's something we can open it up, but that's going to be a long. If you want to do that, we can do that, and then we'll differentiate with respect to the parameter that we have. And when we do that, we are going to be able. Okay, that's what we have here. So the aim is we are trying to find the minimum square because we're trying to reduce the sum of square of our error. So we're trying to minimize that, and when we solve this out, we are going to estimate our beta one, okay, which is sum of xi. This is like deviation across each one of them divided by the square of the deviation, okay? And then from that, we are going to get our beta hat naught to be y minus beta hat 1 by x. Now, if you go here, that one is straightforward because for us to do that, you just take the expected value of each one of them, and then remember that this is going to become 0 anyways. So, and this is going to be the estimated beta 1. Okay, maybe I'm going to make a separate video just to prove it, and then we can attach it as part of our video. So at the end of the day, we are trying to say that when we minimize our sum of square, we're going to have our beta hat to be summation x minus bar x, right? And y minus bar y over summation x minus bar x whole square. Okay, and then our beta, so this is going to be our beta 1, and then our beta naught is going to be bar y minus beta hat 1 bar x. Okay, so that's what we have right here. That's what we have right here. So that means manually, if we want to solve for our beta one, we just plug in the mean of their respective value and remove it from individual predictor and the response. And then we take the square of that and divide accordingly to get the estimate of our beta one. And we do the same. That means we must have gotten the estimate of beta one before we can get beta naught. Don't forget that. All right, so the next thing is how do we do this in R? Because this, imagine when you have large number of observations, this is going to be a tedious thing to do. And that way we don't want to keep going back. Of course, that's the essence of having a programming skills to help us build this model to help us estimate for this parameter. Now, for us to estimate the parameter, the first thing you are going to indicate this LM function is talking about is a regression function that we use to fit our model. Okay, so the sales here is talking about what? This is going to be our outcome variable. Okay, so this is the sales, this is the other predictor variable TV. This is the outcome. This sign is what you use. It's just like the way we write distribution and say a particular variable is distributed normally with maybe the parameters. But here we are saying that the sales is we are modeling it on TV. So this, when you want to press this sign, I think is shift on the keypad before your one. And then you press the TV and then you indicate your data, which we already specify in this place. We already said art. So the name of our data is art. So when you come to this code chunk, you indicate the name of your data based on how you have named your data. And then we use the summary function to just call out the summary of that. And we extract the coefficient by using the coefficient function of our model SLR. And that way we can fit our model. All right. So after we have fit our model, let's say this is what we have as our regression equation. So now we have estimated for beta naught, we have estimated for beta 1, and now this is our predictor variable, this is our outcome variable. Now there's going to be a difference between this y that we had before and this y hat because this is showing the predicted the model equation. Okay, so it's showing that the y, which is now the sum of the sum of the intercept with the slope multiplied by the predictor variable TV. And that way, if you want to interpret this, we would say that, of course, for the baseline, we usually call this a baseline because is the predict is the intercept, right? So for the intercept, we call it the baseline because it's just, we don't even test for the significance of this, whether you like it or not, we just put it in the model, okay? So, and that way we can say, oh, the beta naught is 7.03 and the baseline sales when the TV is 0. We call it baseline because it ignores the predictor. Okay. So, and for us to estimate, to interpret our beta 1, we already know the estimate of beta 1 itself is 0.048, right? And because it's a positive value, you can say on the average, because anything you want to say, you have to, I'm going to edit this and make sure I put that. Is very important because on the average, a unit increase in TV, right? A unit increase in TV will lead to an increase of 0.048. And in fact, you can add that to 7.03 so that you can connect it to the outcome variable itself. Interpretation is very important because at the end of the day, your analysis, you want to communicate it to people that may not necessarily be in your space, be in your field, and you still want them to properly understand what you are doing. All right. So on the next one is we can also visualize our regression line. We can show the scatter plot and add a regression line to show the line of best fit on the model. So this, we are going to have another section talking about the coding. We are going to show the coding in the R. We'll run it and then I will explain better. All right, another thing we do is we do what we call a diagnostic check on the residual. And that's because I talked earlier that the residual part is accounting for all other variability that cannot be explained by the predictor variable. Okay, so and of course, from the model itself, remember the model is what? Is saying that y is beta naught plus beta x. But remember, when we write this out, we're going to have bar y minus the Heston. When you fitted the model, what do we have here? Let me go back. Here, this is where we have the y hat, right? So when you try to estimate this, we are going to have yi minus. So for us to find the residual of each of our each of our inputs, we are going to take the fitted model from the individual observation. This is what I'm saying. So E high in this case is going to be, let's change this to a different color. So EI is going to be each observation minus the predicted observation. Remember that our y hat is what? Is beta naught plus beta 1 x. Don't forget that we already estimated for our beta naught, we already estimated for our beta 1. So when we substitute that, that means we're going to have a new y hat based on our model. And then for us to do our error, for us to obtain error of each of our observation, we have to take that away from the input. So that's what this is saying. So if we come back here now, we are going to have a new set of numbers for the error term. And then with that, we can start checking the assumptions. We can start checking like the linearity, the homoscedasticity, and the normality. Also, we can check for if there's an outliers in the data, like we use the Cook's distance. We can also compute the metrics for the error term, like the mean square error, like the root mean square error. We have a couple of them that are like assessment metrics for the error term itself. All right. So we can also do this is the hard code for visualizing, for doing this diagnostic check that we just talked about. This is going to give us about 4 plots, and then each one of them is talking about the linearity, the homoscedasticity, the normality assumption, and also the Cook's distance. Okay. So when we do this, we are going to explain further. Now, why do we need to compute the coefficient of determination? This is the metrics for the fit itself, the model itself. And that's because we want to know how much variation, how much is our model explaining, what is the proportion of the variance that is being explained by our model. We want to know that. And that's to test the performance of our model. All right. So, and we're going to do this as well for in the R code, and then that way we can explain. Now, the next thing is we want to test the hypothesis. We want to know the significance of our predictor variable. Don't forget that in this case, we only have a single predictor because it's a single linear regression. But when we go to the multiple case, we're going to do this for each of our predictor variable because we want to know whether they are significant. It's one thing to estimate the model. It's one thing to estimate the parameters in the model. It's another thing to test for the significance of the predictor. Those are two different things. Here we only estimated for the intercept and the slope. And that's because we're trying to build a relationship between our outcome variable, which is a continuous variable, and our predictor variable. And at the end of the day, we want to be able to interpret the relationship. Another thing we want to do is we want to test whether this TV is actually significant. What do we mean by significant? We want to know whether he has any influence, whether he has any effect on our outcome variable. And that's what this section is talking about. Okay. So now how do we test? We are going to use a t-test because we are doing an individual test for the parameter. And this one is talking about the standard error of our estimate. This is our estimate. You are going to take the estimate, and then this is our degrees of freedom. Okay, so this generally we write it as degree of freedom is n minus p, and our p is talking about the predictor including the intercept. Okay, that's why we have two. Remember that we only have just one predictor, but now we have the intercept which is b naught. So when we put that together, we're going to have n minus 2 as the degree of freedom. And some of us that we do have access to statistical table, you can do that, and we can also check the critical value here. We're using our R. So we can use our Q norm, we can use our QT function because we are doing the T distribution. So we can use the QT, and remember that our if we look at the normal distribution, our T distribution, we are going to use is always to the left when we are picking the critical, when we're looking at the critical value on R. So the P is always showing to the left. So we're going to pick n minus 2, then we have to pick our level of significance, especially when we take it further and we start doing like confidence interval and all of that. So we can easily check our critical value and we compare that with the calculated value. And then we have our decision rule to help us make a decision that when our p-value is less than 0.05, we are going to reject H naught. Otherwise, we fail to reject. And what that means is that predictor is significant. Now, if we do that, we are going to see that there's a strong evidence that our TV ads actually impact the sales. We will visualize this, and then we'll go into R for the next section and demonstrate each of this, and then it will help us to better understand that. Don't forget, if you have any question, you can always reach out on our classroom, and then we can have like office hour to properly address that. See you guys.